This is Lecture 17, Slide 1. We now begin the cosmology portion of the course. We understand gas and dust, how stars form and evolve. We understand different types of galaxies and what they look like at high redshift. And now we want to think about the universe as a whole. What is its ultimate evolution? So on Slide 2, we have the fundamental questions of cosmology, which are: what is the value of the Hubble constant, and is it changing with time? Slide 3 indicates why the Hubble constant is important. We've already seen from the Hubble-Lemaitre law that you can plot a galaxy's velocity as a function of its distance from us, and we have a straight line whose slope is called the Hubble constant. So to first order, we have on this plot a straight line. The velocity divided by distance is the Hubble constant, so we can invert that and say that the distance divided by the velocity is 1 over the Hubble constant, which is a time, because the units here on the y-axis are kilometers per second, on the x-axis they're distance, and so we have a distance divided by a time divided by a distance. So 1 over the Hubble constant is a time. It's the first order approximation for the age of the universe. And so it's called the Hubble time. This would be the age of the universe if there had always been a constant expansion rate. So let's take one of the popular values today for the Hubble constant, 71 kilometers per second per megaparsec. And I say one of the values because it's within a couple kilometers per second of this value, but it keeps changing practically every year with new observations. So about 71 kilometers per second per megaparsec, we can calculate what the Hubble time is if we convert to self-similar units. So we have a megaparsec times 3 times 10 to the 18th centimeters in a parsec times a million parsecs in a megaparsec. And now we have h naught is 71 kilometers per second times 10 to the 5th centimeters per kilometer. So we put everything in the same units. We end up with 4.2 times 10 to the 17 seconds, which is 14 billion years. So that's the first order guess for the age of the universe. Now, if the Hubble constant were 50, then the universe would be 20 billion years old. If the Hubble constant were 100, then the universe would be 10 billion years old. So because the age goes inversely with the Hubble constant, bigger Hubble constant gives a younger universe. When I was your age, astronomers couldn't decide between the two values of 50 and 100. Alan Sandage favored the value of 50, and Gerard de Vogelaars favored the value of 100. And you know that these were the two famous galaxy morphologists of that period. So a large reason that the Hubble Space Telescope was launched was to try to figure out the Hubble constant. So I said before that a key reason was to look at Cepheids in nearby galaxies. And that's true. We want to get distances to objects very precisely, and that helps us set up the Hubble-Lemaitre relation. So let's see what we can explore in considering how the universe evolves. We first of all start with the cosmological principle, which says that the universe is homogeneous and isotropic. If we don't accept this, then the course goes no further, because we have to have a starting point. And the starting point is that the universe is the same everywhere. That's what we mean by homogeneous. And the second is that it's isotropic, meaning the same in all directions. We can test these ideas, but we start by assuming them, because otherwise all the Hubble-Lemaitre law says is that galaxies are moving away from us. So unless we're a really special place in the universe, then in fact everything is moving away from everything else. So let's see what we can test in these ideas. If they're both true, that the universe is the same everywhere in all directions, then that means there is no center to the universe. There is no center. That means everything was at the center initially and space expanded. So everything's expanding away from everything else. It seems a little confusing at first. You think, okay, if the universe was very tiny and it's expanding, it seems like you could point to a spot where it all started. But that's not true, because when it was a small space, that's all there was. Imagine an infinitesimally small space, and then it grew. So it's not sitting in some super space. it's just a point, that's all there is, and then it grew. So everything was at that central point, and then the universe expanded. So that's what we're working with. Right, so let's talk about these ideas of homogeneous and isotropic in slide 5. What does this mean to be homogeneous and not isotropic? Well, homogeneous is the same everywhere. So here we have a bunch of arrows, and everywhere we're standing, we see these same arrows. So that's homogeneous. We could stand on any one of the arrows and see all the other arrows in the same way. However, it's not isotropic because it matters which direction we're looking. If we're looking up, we see the arrows pointed one way. If we're looking down, we see them all pointing one way. And so there's a preferential direction. And isotropic means the same in all directions. So that's homogeneous. It's the same everywhere. But it's not isotropic because there's a directionality to it. In the middle, we have isotropic but not homogeneous. It's not homogeneous because you see we have 3 different layers there with slants one way and slants another way and then dots. And so it depends on where we're standing what we're going to see. So it's not the same everywhere, so it's not homogeneous. It is isotropic because we can look in all directions and we've got the same pattern of slants and dots. In the last sequence, we have homogeneous, not isotropic. That really looks the same as the first ball we showed there. And then on the second, we've got isotropic but not homogeneous. We've got a favored point with a gradient moving out from that point, although it looks the same in all directions from that point. But the fact that there's a point there makes it not homogeneous. Slide 6 shows 2 inadequate models for the expansion of the universe. They're inadequate because they're deceptive, but they make a reasonable analogy as a starting point. So one is this expanding balloon model, and imagine that all those little circles are galaxies. And as you blow up the balloon, the galaxies move apart. That's the idea for the expansion of the universe, in which we're measuring galaxies' motions with respect to us because we're standing on Earth in the Milky Way. But if you were on another galaxy, you would measure the same thing. The reason that model breaks down is that you're tempted to say, okay, it's a tiny balloon, it gets bigger, and I can point to the center of the balloon as the center of the universe that everything's expanding away from. But again, we don't have this structure sitting in a big superstructure, a super universe. This is everything there is, and everything was at a point, and then space grew. So you only look at the surface of the balloon when you're talking about this model. And on the surface, as you blow up the balloon, the galaxies are getting further apart. The lower model is the raisin cake model, and again, there's some point that looks like the center. So just imagine that what we're talking about is galaxies moving apart from each other. So the raisins in the cake will move apart from each other as the cake is cooking. Slide 7, I think, shows the expansion a little better than these 2 models. These are marvelously color-coded dots, with one representing the universe at one time, and the red and blue representing the universe at another time. And so you want to see if the universe is all expanding away from us, or whether in fact you'd see the same thing no matter where you're standing. And so the blue dots are slightly shrunk with respect to the red. If you overlay them, then you see if you're standing right in the middle dot, it looks like the whole universe is moving away from you, going from blue to red, because they're all pointing to you. But now suppose you're standing on another dot, and in the right hand side, you're standing in the lower right quadrant. And now it looks like everything is moving away from you. So all you've done is taken the 2 sets of dots, blue and red, and expanded one with respect to another, and overlay it on any dot you want to. And no matter where you're standing, the universe seems to be moving away from you. So that's the idea behind the Hubble-Lemaitre law. The galaxies we measure moving with respect to us, but in fact, no matter where we're standing, we would measure the same thing. Slide 8 shows the same idea with a cute little Martian. And the point is that no matter where you are, no matter what galaxy you're standing on, anywhere in the universe, you would measure the same Hubble constant because you would measure the same velocity as a function of distance, the same slope that we measure locally. So suppose we're the tall pink person on the top view, and we're in the Milky Way galaxy, and we're measuring galaxies near us. And so, in one direction, we see a galaxy moving. In this case, the model shows a Hubble constant of 73. So we see a galaxy on the left, a megaparsec away. Abbreviated incorrectly, it should be capital MPC as it is in the lower diagram. Anyway, megaparsec in one direction, we see the galaxy moving 73 kilometers per second away from us. As we look in the other direction, we see another galaxy moving 73 kilometers per second away from us, also a megaparsec away. And now we go to where the little alien is. I guess he's not a Martian if he's in another galaxy. Anyway, he's looking, and he would see a motion away from him of 73 kilometers per second for that first galaxy. And if he's looking at us, we're 2 units away, 2 megaparsecs, so he sees us moving 146 kilometers per second. We see him moving 146 kilometers per second. So no matter which galaxy we're standing on, we're going to measure the same motion of galaxies near and far. The bottom graph is the same idea. Suppose we're at galaxy A, or we're on the Milky Way. So what do we measure? The Milky Way sees galaxy A moving 750 kilometers per second if it's 10 megaparsecs away. This is with a Hubble constant of 75. Galaxy B is 20 megaparsecs away, so we would measure 1500 kilometers per second. But B compared to A is only 750. And C compared to us, we would measure 2250 kilometers per second. But A sees C moving at 1500 kilometers per second because it's only 20 megaparsecs from A, whereas it's 30 megaparsecs from the Milky Way. So that's, again, what's behind the Hubble law, that there's nothing special about our place in the universe, that anywhere in the universe we would measure this expansion. Slide 9 talks about what's known as the steady state model for the universe, also known as the perfect cosmological principle. This was an idea that was proposed by Gould, Bondi, and Hoyle, three famous Cornell astronomers in the 60s. And so they were imagining, okay, if the universe is homogeneous and isotropic, that is the same everywhere in all directions, let's add one more component and say it's the same for all time. Now, they allow for an expansion of the universe, but in this model, the density would be the same for all time. And that requires that there be constant matter formation. If the universe is going to expand and keep the same density, then you've got to have more mass if the volume is getting bigger. And you say, well, that sounds pretty crazy. How do you make matter out of nothing? Well, in fact, that's what the universe is doing, as we'll come to later. We've got some energy associated with the universe, and eventually we're going to get matter out of it. And we know that E equals mc squared, this sort of thing works. And so we'll talk about what the universe is doing later. So in their model, the universe just keeps making matter. So it's a constant density. It's still an expanding universe. So this was in favor for a while. And then as an alternative model, George Gamow was saying, well, you know what, suppose the universe is expanding, but it doesn't fill in with more matter. As it's expanding, it would get less dense, but also if it's expanding and was hot initially, it would cool because any expanding gas will cool. And Gould and Bondi and Hoyle said derisively, well, what is this model, like a Big Bang? And he said, yes, that's exactly what it is. And so it came to be called the Big Bang model. So in this universe, we have an initial universe that's infinitely tiny and hot, and that's the primeval fireball. And the universe expands and cools. And there are various stages here that we're going to be talking about later. But the point is that this model has a very different consequence than the steady state model in that it's cooling as it ages. So this ought to be something that's testable. Slide 11 shows Penzias and Wilson, who were two astronomers who were trained in electrical engineering. And they were working with Bell Labs back in the days when Bell Labs was a big research institution. And they were looking at communications. They had this big horn antenna that you see in back of them, and they were postdocs, and they were trying to get rid of noise. They kept getting some kind of noise that was interfering with their communications, and they couldn't trace back what it was. Finally, they went to the horn thinking maybe it was filled with bird droppings, which it was, and they cleaned it out thinking maybe they'd get a nice clear signal, and they kept getting something they couldn't get rid of. And it turns out they discovered the cosmic microwave background radiation. That's a radiation that results from very early stages of the universe, as I'll describe, coming from a time when the very first atoms were made. They didn't understand what they were looking at, but they later realized what it was, and they ended up getting the 1978 Nobel Prize for their observations. And so on slide 12, we see a plot of the brightness as a function of wavelength, and they were looking at millimeter waves, and they see that there's a peak. And it looks sort of like a black body curve. You see those the red line there for the observations, but it's not a very nice looking black body curve. But if it were a black body curve, you could calculate the temperature, as you know. And from that peak, they would get 3 degrees. So they were puzzling over what this meant when, in slide 13, um, they called up a friend of theirs, Bernie Burke from MIT, who that day was having a lunch with Peebles, Dickey, and Wilkinson, and another astronomer not shown there, Peter Roll, who were all at Princeton for a brown bag lunch. And I'll continue the story next time. We continue with lecture 17, slide 13. We left off where Penzias and Wilson were contacting Bernie Burke and the other astronomers listed there, who were at Princeton talking about how they might be able to detect a radiation from the early universe. So they had the theory behind what would be happening if they had not a steady state model for the universe, but a Big Bang. They recognized that if the universe is expanding and cooling, that ought to be measurable. So they were trying to figure out ways that they could detect the cosmic microwave background. These astronomers all played a very large role in what follows later, with a lot of significant work related to the cosmic microwave background. Jim Peebles went on to win a Nobel Prize last year. But for now, let's continue the story. They were talking to Penzias and Wilson, and Bernie Burke said, "What, it looks like blackbody radiation? What, you got a peak at about 10 degrees? Oh, that is just right." Because that was close to the 3 degrees that they were trying to seek in understanding expansion and cooling of the universe. And so they got scooped by Penzias and Wilson. So what does it mean? Slide 14. What is this cosmic microwave background radiation? These are photons from the early universe. When the universe expanded and cooled, at that moment, the photons and particles were said to be coupled. That is, the photon energies were high enough that the atoms that tried to form kept breaking apart. That is, at that time, that turned out to be 300,000 or 400,000 years after the Big Bang, so in the very early universe, there were protons, there were electrons, so they tried to get together to make atoms. And there were photons with enough energy that it kept breaking apart the atoms. And so there were atoms that would form and then they'd be ionized, and that happened over and over again. So in that way, photons and particles were coupled because the photons kept being absorbed by the atoms that would then break apart. Eventually, as the universe expanded and cooled, the photon energy was redshifted enough that it was too low in energy, and the atoms therefore couldn't absorb them because they weren't energetic enough to break the bonds. So the atoms stayed as atoms, and then the photons then traveled on. So they streamed freely through the universe. And this is the light that we see today as a cosmic microwave background, and we see it at a temperature of 3 degrees. But it traces back to when the universe was 300,000 to 400,000 years after the Big Bang, when in fact the temperature was 3,000 degrees. This is known as the age of decoupling or the age of recombination. Decoupling because photons and atoms then were separate, photons could travel freely, or recombination because when the atoms kept breaking apart because they were ionized, then finally at this stage the electrons could reattach and make atoms. So the age of decoupling, the age of recombination is when the first atoms were made, and that's the origin of the cosmic microwave background radiation. In slide 15, we show the process. So the universe expands and cools so photons could no longer break apart atoms. On the left, before recombination, we've got the photons, which are energetic enough that they kept the protons and electrons apart. Every time they tried to form an atom, they'd be broken apart. But on the right, after recombination, those photons didn't have enough energy. So again, decoupling, recombination, first atoms being made. This happened at a temperature of 3,000 degrees at a time about 300,000 years after the Big Bang, and this corresponds to a redshift of 1,000, and we get that from the ratio of the temperature then to the temperature now. Slide 16 shows again what's going on. We've got photons decoupled from the atoms, and they are the photons that come to us today as a cosmic microwave background. So it's the radiation that had its origins in the early universe at the Big Bang. So already by Z of 1,000, 300,000 years after the Big Bang, the universe had considerably cooled. So temperature of 3,000 degrees then and 3 degrees now. On the left, we're at the present at the bottom of the inverted triangle. And so we're looking out and we see galaxies and we look further and further away to the point where it says 3,000 degrees right at the lower red part. It says CMB last scattering. And in fact, we cannot see past that. We don't get any information earlier than that because the photons were trapped by the matter. So it's like looking at, on the right, looking at clouds, and we're not able to see uh, the stars through the clouds because the light is trapped. And so earlier than decoupling, the universe is said to be opaque, and afterwards it's said to be transparent. Slide 17, we know that the observed wavelength over the rest wavelength, that is the wavelength that was emitted, is 1 plus the redshift by definition. For blackbody radiation, we have the radiation goes inversely as the temperature. And so that's how we get what I already said, that the temperature then divided by the temperature now is about is equal to 1 plus Z, but that's about equal to Z if we have a very large Z. So 3,000 degrees to 3 degrees, that's the redshift of 1,000 where we're seeing this radiation. Slide 18 shows a phenomenal plot that resulted in a Nobel Prize. And this is a result of observations with a cosmic background explorer that was a satellite that was sent up to detect in more detail the 3-degree radiation. And so this was a plot, a black body radiation plot of brightness as a function of, it should say, wavelength at the bottom there. And so this is our familiar black body curve, and the peak corresponds to 3 degrees. Now, what you can barely see is that the red line is from theory for a black body curve, but the open circles are the actual observations. And when this was presented at an American Astronomical Society annual meeting, I got a standing ovation because everybody realized that this shows, yes, the idea of a Big Bang is correct because we have a universe that expanded and cooled. Steady state model cannot account for this change in temperature. Slide 19, we see some more results from the Cosmic Background Explorer satellite. We see that as we look in one direction or another, we're going to see a slight blue shift and red shift shown here. And that's because we're moving in the sky. And so we need to remove this motion so that we get what the universe is doing and not because of our motion in it. So you remove that, and then in slide 20, there's another bit of radiation that you have to remove, and that's the radiation at these wavelengths from the Milky Way. And so if you're going to look in the infrared in millimeter wavelengths, you're going to see radiation from our galaxy. So you want to take away those signals too. So once you remove our motion in the sky and our radiation, then you get what's in slide 21, which is the cosmic microwave background radiation, which is a really interesting plot. The universe is 3 degrees everywhere, but there's a plus or minus to the tune of 1 part in 10 to the fifth. 1 part in 10 to the fifth. So it's 3 degrees, 0.00001 in one direction and 2.99999 degrees in another direction. So at that level, you see a variation in the temperature. 3 degrees everywhere, but slightly hotter or slightly colder in some directions. And what we see here is the large scale structure in the universe. The pink and the blue there, in fact, are outlining the bubble void structure that we talked about in looking at the distributions of galaxies. And so remember that these come from the time of decoupling when the first atoms are made. So they're showing the imprint of where there's slightly more or less matter in the universe, just random fluctuations. And we trace out the scale over which we now see the bubble void structure in the universe when we look at galaxies. So slide 20 shows John Mather and George Smoot, who are the ones that won the Nobel Prize in physics in 2006 for their discovery of the black body radiation using the Cosmic Background Explorer.